Hey y'all, welcome back. This is technically lecture seven, although who knows what order they're in at this point. I think this will still be lecture seven, and it's focused on correlation and linear regression. So last time we talked about t-tests, and we talked a lot about the normal distribution, the standard normal, the z distribution, the t distribution. It was a lot, but it also is kind of the basic theory behind all of the stats we're going to learn. So the good news is once you have the idea for taking basically any distribution and making it into a standard normal and then applying some sort of Z style or T style distribution or score to your data, kind of all set. They're all the things we're going to learn are like that. So today we're going to talk about correlation and linear regression. And I know I said that t-test is kind of a precursor to the analysis of variance or to ANOVA, which we're going to talk about next class. But I think it's really important to point out also that the t-test is a really, really simple use case of what we call parametric statistics, which is comparing groups of things to other groups of things. And correlation and linear regression are the same thing. They're very much a relatively simple way to look at comparisons between different things. And especially linear regression, it runs on the exact same idea as the t-test. And truth be told, a linear regression and a t-test, they're the exact same math. And we'll talk about how and why they're slightly different in this lecture. So let's have a look. Let's have a look at our slides and we'll get going. All right, here we go. Correlation and linear regression. First, what's a correlation? Maybe you have some ideas of this. I'm certain that you've heard this term before. My audio's clearly not working. Hang on. Okay, we fixed it. I think it might have been working anyway. So, correlation. You probably have heard this term before. You probably have a sense for what it is. You've probably also heard correlation is not equal to causation or some such phrase. And that's true. But hopefully, when you think about correlation, you think of like when one thing changes, another thing changes. There's some kind of relationship between one variable and another. So the way we define it according to our text is two numerical variables are associated in some way. The key here that makes this different from other ways of thinking about data, we're talking about the relationship between two numerical variables or two continuous variables. That means there's no categories on X or Y. We have numbers and numbers, and we're looking at the relationship between this set of numbers and this set of numbers. So we often think of correlation as being positive or negative. And we'll talk a little bit more about this, and you'll be able to have a sense for this, but positive and negative correlations exist. What does a positive correlation look like? What about a negative one? Think about that. So maybe pause the video, draw each, and see if you're right. We're going to dig into this in the next couple of slides. And I'm not going to give the answer away. So we'll get to it, but it won't be for like a couple of slides. So go ahead and draw out what you think positive and negative correlations are like. And we'll see if you're right. Probably are. Well, let's check. All right, next up, we need to know before we get going into correlation about the linear correlation coefficient. And this is where we learn about the strength and direction of our relationships. So the linear correlation coefficient measures the strength and direction of the association between two variables. We call it R. Hopefully this is starting to sound kind of familiar because you've probably got in your past, you probably looked at a linear regression or a correlation and said, well, there's a relationship here defined by R squared. This is the square root of R squared, known as R, right? So how do we calculate R? And this is where we realize like the programming language R is again our friend. R is calculated as this complicated math. So we have numerical variables on the X and numerical variables on the Y. So we're looking at the sum of R sample minus the sample mean times on the X times the Y sample minus the sample mean on the Y. The sum of all of those values of all of our samples or all of our individual, all of our individual samples divided by the variance of each of those things. So that's the sum of the difference between what we measured, and the mean squared. Square root of the sum of the square of the difference times the square root of the sum of the square of the difference. So that is, again, it's a correlation between x and y, and it's basically the two means multiplied together, or the difference between the samples and the means, so the variance divided by the standard deviations. That's R. Okay. In case you need some math, if you really want to do this math, here's the symbology. X is numerical variable number 1 on the x-axis. Y, numerical variable number 2. I is an individual observation. X bar and Y bar are the mean of those variables. So we're taking the sum of the products, how deviations in X and Y vary together, and we're dividing that by the square root of the sum of squares for X and Y. Sum of products and sum of squares, those are important concepts in how we understand linear regression. And I'm just introducing them to you. We're not going to dig deeply into them at this very moment, but they are there. So R, it's this complicated math that sums up to sum of products divided by sum of squares, square root of the sum of squares. Okay, now here's where we learn about whether you were right about your correlations. Okay, here we have our X and Y, and we can see a positive correlation here and a negative correlation here. Sorry, that is not correct. Positive correlation would be as one increases, the other increases. Negative correlation would be as one increases, the other decreases. Okay, cool. What you're seeing here is a measure of how points vary in space. Here's X and Y. We have positive deviation in X, pushing data this direction, positive deviation in Y, pushing data this direction, negative deviation from the mean in Y would draw data down, negative deviation from the mean in X would draw data to the left, right? So you're looking at these differences in this relationship, and that drives your data in different spaces. I find this graphic, which is in the text and is recommended as a way to describe linear correlation coefficient, to be a little bit confusing. So if you're just like, what does that mean? That's okay. Just recognize that the correlation coefficient is a measure of the relatedness of X and Y, and it's sum of products divided by the square root of the sum of squares. All right, let's carry on. All right, now, what you also probably know about correlation, it's all probably based on R squared, but I bet you've heard the more it approximates a 45-degree line, the closer the R squared is to 1. That is true of the R as well. The better the correlation is, the more obvious the trend is, the better the correlation is, right? So here we can probably go ahead and draw some correlation lines. We'll start with the easiest one here. This is a pretty clear correlation, positive correlation between X and Y. Here's a negative correlation, whereas X increases, Y decreases. This is a positive correlation, but it's not the best fit. And then who knows what this one is? It doesn't look very good. Okay, so pause the video and estimate what you think R is equal to. R has to range between 0 and 1. No correlation is 0, and 100% correlation is 1. So guess for each of these. Remember that this line that I drew is estimating a line of best fit, and we're going to dig into how that works and how to do the math here in a minute. All right, I'm going to start talking through the answers. So if you haven't done this yet, you should pause and try to come up with your own answers. First one on the left, there's basically no correlation. I just say R equals 0. Turns out that's pretty true. This middle one, second one from the left, there's a positive correlation. It's, fine. What do we think? R equals 0.5. So there's a correlation, but it's not super, super good. There's plenty of other noise. The negative correlation that's next is a little bit better. So I'd say like 0.7 or 0.8, and it's 0.7. It's negative 0.7, telling us that it's a negative relationship. And then the last one is close to 1, and it turns out that R equals 0.9. So that's pretty good. All right. So how do we do correlation analysis in R? We're going to do this in class, but it's real easy. Here you go. You want to try it in R? You can do it now, or you can do it in class. You open up an R script. You pick a data set. MT cars, Palmer penguins, iris, whatever you want. Choose two numerical variables. You know how to find whether a variable is numerical at this point. And you actually just run a function called core. So core is really easy. You'll just say core. I want to know the correlation of whatever the name of the data frame is, $sign, the name of column number one, comma, the name of the data frame, $sign, column number two, right? So you're just telling it, look in this data frame for these two columns, do my correlation. It produces an R. That is it. That is all it does. Really, really easy to get a correlation in R. Really, really easy to get an R squared as well. But that is not what this is. Correlation analysis just produces the R. We're just looking at the correlation of the points. We're not drawing a line of best fit. That's the difference. Now, what if we want to test a hypothesis with this? Because that's generally our point. We might be interested in, is there a correlation between X and Y? So we calculate the correlation R between two variables from a sample of our population. The actual correlation between X and Y within our population is denoted as rho. So the H naught for a hypothesis test of zero correlation is rho, or the true correlation of our data is zero, right? Our H naught would be that it's not zero. We calculate R in this complicated way, or by using core. Then we need to calculate our standard error, which we know how to do. It's the square root of 1 minus R squared, interesting, divided by N minus 2. Notably, in this case for correlation, we use N minus 2 because we're even trying to be even more conservative with our estimate than we would if we were doing a t-test. And then you are doing a simple t-test. T is just R divided by the square root of R, or the standard error of R. So then we would use a table to calculate P from T, or we could do a t-test on our correlation. This is basically never really done. We usually want something a little bit more complicated than this, but now you've seen it. The assumptions for correlation are as follows. We have random samples, just like before, and the measurements have a bivariate normal distribution. What does that mean? It basically means we have to have a relationship between X and Y that looks pretty like linear. You do a visual check of a scatter plot and you look for this kind of thing. Like it looks like some kind of linear analysis, like some kind of linear relationship. If you've got some variables that are like way down here, some data that's like way down here, way up here, even like over here, those are going to be maybe outliers, and we want to check for those because when we try to draw a line of best fit, and we got those outliers in there, we might get something like this. And really, the reality of our relationship without those outliers is that we get something pretty neat like this. So we've got to be careful. All right. That's correlation in a simple way. Correlation is really simple. It's a nice way to see, are these variables related, yes or no? To be honest, we're almost always going to do linear regression here instead. So this is really just a precursor to learning linear regression. You should also know, though, that there's two different ways to do correlation. One way involves doing correlation with the real numbers. But if we have bivariate normality, that works great. But if we don't have bivariate normality, we can standardize our values by doing something called Spearman's rank correlation. It again measures the strength and direction of a linear association between two variables, but it's robust and doesn't require bivariate normality. This is a little bit more complicated, but it's pretty simple still. The Spearman's rank is a test of H naught of no linear correlation. The test runs a correlation analysis using the ranks of the data, not on the data themselves. So let me see if I can draw one out for you, what an example is. If I have data, and just, it's not going to be X and Y. I'm only going to give an example with one number. And here's my real data. I'm a great user of the mouse. And here's my rank. Yeah, judge me. It's fine. Please laugh. What if I have like 1, 7, 11, 15, 15 totally, and 21. You can convert these to rank by just doing this. 1, 2, 3, 4. You make a rank ordered list, right? So we change our real data that might have whatever distribution they have into rank ordered lists. And you can do this for the X values and the Y values. You can rank order them. And then you take the ranks of the data and you run your correlation analysis on those. It's exactly the same to calculate R as before. Using the ranks standardizes the data into what will essentially become an approximation of a standard normal. Okay, so the only difference between this and regular correlation is that we rank the data instead of using the raw data. We just do the exact same thing. And then we say we have 100 samples for T. When N is greater than 100, we use the following math for Spearman's rho, or Spearman's correlation. T equals R divided by S, the standard error of R. This is what we used for T before. So you run a core.test to do Spear. So Spearman is core.test instead of just core. And you can define it with method equals Spearman. So if you just do core.test without method equals Spearman, it'll default to a regular correlation analysis. So we're going to use core.test, and we're going to say we're using the Spearman's rank, or we're trying to calculate Spearman's rho. And that's it. That's Spearman's. So now you've learned correlation in 2 different ways. And Spearman's is the robust one. Let's move on to linear regression. All right, linear regression time. A linear regression, something we probably have all heard before. Maybe we've never done the math before, and that's totally okay. But a linear regression allows us to predict the values of one variable based on its relationship with another. So if we know the relationship between X and Y, we can predict anywhere within the bounds of X and Y where new data points might land. Linear regression is based on the line of best fit. A little different from correlation, where we're just looking at the raw points and are the points related, yes or no. In this case, we're drawing a line of best fit through our data and calculating how well does this line fit the data. All right, linear regression works like this. We need to draw a thing called the least squares regression line. Most of us call this the line of best fit. It's called the least squares regression line for a reason. We're going to unpack why here in a second. The least squares regression line is the line through our points that makes the squares of the deviations of points to the line the smallest. Oof. Okay, so it's called the least squares regression line because it's a line we draw through our points that makes the square of the deviation of those points to the line the smallest. So you can see how this works. Here's an example. The left box here shows large deviations from the line. Each of the points has a really long tail to connect it to the line. That means we have really large deviations. So we're going to have really large squares of deviations. So this is not the line of best fit or the least squares regression line. The best way to draw a good line, right, approximately, is to get as close to every point as possible and stay in a straight line. You've probably learned that before. Maybe you never learned this complicated math before that we're going to talk about, but that's the general concept. So you can see as we move to the middle panel that we have smaller deviations. Some of the points are really right on the line. A lot of the points are closer to the line, but the line still isn't really accounting for those top points. So I want you to recognize 2 things here. One, values that are really far away from other values can really drive the line into a different direction. So we want to make sure we understand what is and what isn't an outlier and what is and what isn't good data. The second thing is that this line, while better than the other line here, better than this line, like this, which has really large deviations, is still not the best because especially of these and these high points. So we'd want to try to maybe move our line so that we can account for those high points a little better. Things are really good through the middle here, so we can go like that. It's not a perfectly straight line, but you get the idea. And that's what we end up at the far right, with the line that has the smallest deviations. The overall smallest deviations comes from this line, so this is our favorite line. This is the line of the least squares regression line, the line of best fit. Okay. The way that you calculate the deviation is, of course, just taking the value and subtracting it from the mean. For every single one of these, which is a lot. Sorry, so subtracting it from the value at the line. Okay, so how do you calculate then the slope of the regression line? Hopefully you got this one. Hopefully you know how to calculate slope. If not, here we go. Y bar equals A plus BX bar, where Y bar is the mean of Y, and X bar is the mean of X, essentially. All right, Y, that's our response variable. A, it's the y-intercept. You've probably seen this denoted as AX plus B. I recognize that is another way to look at this. And I'm sorry that the textbook uses A plus BX. I think that that's kind of annoying. But nonetheless, I'm trying to use the same the same notation as the textbook so that when you refer to the textbook, you don't get confused. All right, so y equals a plus bx, slope of the regression line. Y, response variable. A, it's the y-intercept. It's the value of y for when x equals 0, right? You call it the y-intercept because if this is x, x equals 0 here, and if we have a line like so, this here is our y-intercept. So it's where x equals 0. And b is the slope of our regression line, which is the change in y per unit x. And you've probably calculated slope a lot of times in your life, so I'm not going to belabor this point, but you calculate slope by calculating slope. It's the sum of the difference between all the points divided by the sum of the variance of x. It's rise over run also. It's the same way it always has been. This is just if you're looking at it from a statistical standpoint. Okay. Now, when we calculate slopes, it tells us something about the relationship. If the slope is positive, like this, the line shows a positive correlation. If the slope is negative, it's a negative correlation. If the slope is 0, there's probably not a relationship. Now, two things can vary on these lines, the slope and the y-intercept. Those are the only things that can change. These x and y's are kind of the same. The slope can change. The y-intercept can change. And those are the things that change our relationships. So these first three, they show how the slope can change and how that affects our relationship. But if we have, let's say we're looking at regression of X versus Y variables. Let's say we're looking at penguins and we have two different species of penguin. We have the red penguin and the white penguin with the red outline. So we have this penguin here and this penguin here. Two species of penguins, and X is flipper width and Y is flipper length. And we're comparing the relationship between flipper length and width. We can see here basically that the relationship is roughly the same, right? There's a positive relationship in both species of penguins, and it's roughly the same. But one species has higher Y than the other, which basically means that it's bigger penguins. Same relationship, just bigger penguins, right? That's going to become really important for us at some point here. So just recognize that when you're thinking about linear regression or linear modeling or anything that involves linear relationships, the things that can change are the slope and the intercept. Okay. Importantly, the value of y from our regression line estimates the mean value of y for all individuals within the same x value. Okay. So we're getting into some complicated stuff, and I just want to acknowledge that and take a breath. We're going to talk about a concept of residuals, and residuals are going to look and sound a little confusing, but they're actually just basically the difference between your points and the regression line. Okay. So the residual measures the scatter of points above and below the least squares regression line. It's the difference between each data point and the line of best fit. Here's how you calculate it for every individual point. So if I have a line and a bunch of dots, right? Bop, 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 dots everywhere. Okay, here we go. We got all these dots. This distance here, that's my residual. This distance here, residual, 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 residual. And all I'm doing is calculating basically the difference between my individual point and the value of y at the regression line. And if I want to convert this into a residuals plot, I take it and I just make this line that's not straight, or that's not, well, it's straight. All lines are straight. That isn't vertical. That isn't horizontal. Everything's fine. I take this line here, this line of best fit, this one, that one. I take that line, it's like at a 45-degree angle, and I just flatten it to make it straight horizontal. Okay. If I do that, suddenly I have this new graph, right? Where all those points I just made with the red dots, those are now these residual points here. So all this does, this kind of graph, all it does is flatten out your line and show you just the vertical distance between your point and the line. So this is just a graph of residuals. It's just showing the same data, only it's transformed it into flat. That's it. Okay. So importantly with residuals, we occasionally want to calculate the mean squares of the residuals. That's a piece of the math that we need for later. The mean squares, right? That's the line of best fit, tells us that we have the lowest mean squares of our residuals. So we calculate our residual for every individual, we square divided by n-2 for the sample size, and that's how we get our mean squared residuals. And when this value is the lowest, that's our line of best fit. Okay. We're also going to want to keep this idea of mean squares residuals in mind for later, but it's just a measure of the value of the mean difference between a point and the line. All right. Now, we're also going to want to calculate error for our relationship, as we always want to do. We want to not just show the mean, but also the variance or the error in our measurement or just in our data. So we can calculate the standard error of the slope, and we can calculate the confidence interval of the slope as well. And when we're in R, you can see that we can toggle the standard error and our confidence interval off and on graphically in ggplot. We may have already done that even. The standard error of our slope is that mean squared residuals divided by the sum of the differences, the variance in x squared. The 95% confidence interval for slope, we use a t-distribution two-tailed. We get a critical value for p equals 0.05 based on our degrees of freedom, which is n-2 for all regression. And then we say b minus 2 times the critical value equals the lower confidence interval, and then b plus 2 times the critical value equals our upper confidence interval. So, and that's because we're doing a two-tailed t. So like the left side and the right side are 1/2 of our p equals 0.05. They're each 0.025. So you have to multiply it by 2. But you calculate the 95% confidence interval by getting your critical value for p is less than 0.05, multiplying it by 2, and then subtracting and or adding it to your slope. So if you have a slope like so, boop, slope like that, your confidence interval would be something like this. The dotted lines indicate the positive one confidence interval and the second confidence interval, 95%, right? And it's symmetrical. So that's how you would do that if you ever want to. We're not really going to do that in class, but if you are interested, that's how you do it. Now, what we can do with a linear regression, with this relationship, this line of best fit, is that any value that lies, and I'll draw the graph again, any value that lies between, I need a new color so I don't confuse you. Any value that lies on this line from here to here, any point within that range, even if it's not a known, we can calculate. If we have the x, we can calculate the y. If we have the y, we can calculate the x, right? Because we have this relationship between x and y, as long as we have part of it, we can calculate the other part of it with our known relationship using the y. Wow, using y equals a plus bx, right? Or y equals mx plus b if you prefer. Okay, so we can calculate any missing point here on this line as long as it's like within our top and bottom bounds. But what happens if that isn't true? That's where we get the concept of extrapolation. What is it? What can we do with it? Can we even do it? And what are the limitations? So the answer to your question here is that it's really important to think about, because if we have a value that is not between these points, well, that's not even really accurate. If we have a value that exceeds our current points, which start here and end here, if we have a value that is not between here and here on our regression line, like over here, we can use the relationship that we've generated from the data to extrapolate, assuming that the trend doesn't change as we get lower, what these values might be if they were on the line. But should we do that? We can, absolutely. We understand y equals mx plus b, or y equals a plus bx. It's the same thing. We realize that that's a formula with a known relationship. The question is, if all of the points that we've used to generate that relationship are over here, and the points we're trying to extrapolate to are way over here, can we consider that to be valid? Most people would say no. You have to be really careful with this kind of thing. Once you're extrapolating, you never know. You're outside of your known range. Your relationship could totally change, right? You could have a line that then starts squiggling, or like it could asymptote to the moon, or, forever down, right? So you have to be really, really careful about extrapolating. Unless you know enough about the system, you probably don't want to extrapolate. So if you're ever in the lab and you're running a standard curve for, say, trying to measure the amount of protein, that's a P, trying to measure the amount of protein that's in a sample. Wow, I'm just having a really great time here. And this is wavelength of light. If you measure here, 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 and here, and here, and you generate this really easy curve, that's great for you. Because if you have another variable or if you have another point that you measure that's anywhere in that range, right? Our knowns are here on the blue line. Our unknowns are here in the red. We can quantify our unknowns by using the relationship between our knowns. But what if our unknowns are way outside the range, or anywhere outside the range? We really can't be sure if our relationship holds. So if we're trying to run a good assay to understand the relationship between protein concentration and anything, for example, we want to make sure our standards cover the entire range of the possible results, right? So you always want to think about that kind of thing. And I can go through another example in class. The general rule is extrapolation bad. And here's some, we should try to avoid this. The further we get from our known values, the more questionable our values become. Okay. So in summary, don't extrapolate unless you gotta. All right. Now on to linear regression hypothesis testing. How do you test a hypothesis of linear regression? We test whether the slope of the trend line is equal to 0. So basically we're saying there is, or the hypothesis here is that there is no relationship. We use the test statistic T, and T is defined as B minus beta divided by beta naught, which is the slope, or B naught, which is the slope from H naught, right? And that's 0. Okay, I'm having a hard time. Usually equals 0, right? Whether the slope is 0. The hypothesized slope is 0. We do our slope minus 0 divided by the standard error of our slope, right? We can calculate the slope with the regression line with this formula. We can calculate the SE of the slope with this formula. We know the t-distribution requires us, when we're doing regression, to have a degrees of freedom of n minus 2. We can thus solve for t, use the degrees of freedom to get a critical value from the table, assess whether we can reject h naught or not. We can also do this in R. But now you've seen the theory. So this is just an example of a t-test applied to linear regression. So what I'm here to tell you is, like, t-test, that's the same thing as linear regression. T-test is looking at one categorical versus one numerical, and we can apply that same concept to one numerical versus another numerical. We can also use ANOVA to do the exact same thing. We can use ANOVA to assess the difference between two means instead of a t-test. We can also use ANOVA to look at categorical means across any number. So t-test is limited to only 2 categories. ANOVA is robust across many categories. But we can use ANOVA to assess the difference between two means in place of a t-test. It's the same thing. We can also use an ANOVA instead of a linear regression to look for a significant slope. Now, we haven't learned ANOVA yet, so don't worry about it, but we can do it. I'm just here to tell you that they're kind of all the same. So we're going to do some regression in R. Here's how you do it. We use a simple function. That function is called LM. That's simple linear model. LM for linear model. Really easy. We're going to do it a lot in class, but the general notation here will be LM of how Y changes, that's a tilde, by X, right? We're going to have to tell it what data we want. We might give it a name, but this is the simple structure of an LM. Okay. Now we're going to do that a lot in class. We're going to try it out. There's a tutorial on Lyceum on the website that's linked on Lyceum with lots and lots and lots of more information and some examples. For now, let's talk about the assumptions. The assumptions, which are important, are number one, at each value of X, there's a population of possible Y values whose means lie on the true regression line. So basically, we should have a linear regression. We should have a linear relationship between X and Y. To check this, you look at the graph with your eyes and see if it looks relatively linear. If it looks like some other kind of relationship, we maybe need some other kind of regression than linear. At each value of X, number two, the distribution of possible Ys should be normal. So we need to make a residuals plot and see if it looks reasonable, basically. And we can look at what that means in lab or in class. Again, the third is the variance of X of Y values is the same as all the values of X. So this is something called homoscedasticity, homogeneity of variance. We make and check the residuals plot there as well. And I'll show you a couple of ways to test these assumptions. And you can see them on the tutorial on Lyceum if you want. And then finally, number four, at each value of X, the Y measurement represents a random sample from the population. So you're seeing a lot of independence, normality, randomness, all the same stuff. We just have to think about the experimental design here to make sure that we did a good job sampling. Okay, let's test some assumptions. We'll test assumptions as they relate to our previous example of a linear regression. Okay, so we're going to check for linearity of the relationship between area and number of species. We check for linearity by looking at the ggplot that we made with the raw data plus the trend line. So this is actually not our example. This is just an example I'm grabbing. We can use the scatter plot of the raw data if we want, but the trend line helps a lot. So it's really helpful to throw this line in there with geom smooth. We're looking for outliers in our data like this that might show us that we don't have the line of best fit. We might even see that the data fit a different shape a little better than linear. If our data look like a roughly symmetrical cloud of points above and below the horizontal line in our residuals, then we're good. Whoa. And we are going to work through, sorry, having some issues with my slides. We're going to work through an example where we test this stuff in lab. So if you want to try to test it now, you can, but I haven't taught you how to do like the residuals plot on here, but there is code on Lyceum or on the website connected to Lyceum where you can try this out. If not, we are going to try it out in class. I'll show you how it works. It seems a little confusing here, but this at least tells you if you want to try to make a residuals plot, how to read it. So this is how you read your residuals plot. And then here, this is just how you look at your graph. But recognize that like the example I just showed, that doesn't look like a linear regression is the appropriate fit. Okay. Really important, a couple of final slides. The measurement error can really, really impact your line of best fit. So you can see here on the left, we have a really tight line. All of our points are really, really close to our line. The residuals are really small. So we've been very precise in our measurements. They're super close to the line of best fit. Now, biology, as you know, doesn't really care about your hypothesis and is going to be pretty variable. So the more variable you are, the less confident you are in your line, right? So we would say r squared equals like 1. And here we might say r squared equals 0.75, something like that. Now you can get so far away that when you have enough of a cloud, you might be able to draw two lines of best fit that have the exact same values or really close. So we want to be really careful. Here we have measurement error in the y direction that's showing you like just difference this way. And here's measurement variables variation in the x. And you can see that we're kind of pulling our points around this direction. And that's resulting in basically two lines of best fit. So that's complicated. So x is measured with error in the right panel, which causes the expected estimate of the slope to decline. That's the solid line, compared with the slope in the absence of measurement error, right? So the original slope would have been here, but once we added the x direction error, we got a different slope. I actually read that backwards. This is the original one without the error changing it, right? And that's the one we see in the other two panels. And then here's the new one because the x variation has drawn us down. So our correlation is not the same. We have to be really careful with this kind of measurement error. Okay. In all cases, we're increasing the variability of residuals, and that is causing more error. It introduces biases into the estimates of our slopes. All right, you should also know, before we dig into details, nonlinear regression also exists. It's a slippery slope. We're not going to dig into it too much, but if you use stat smooth or geom smooth without method equals LM in a ggplot, you can make any shape, basically. It makes a curve of best fit. Here's a quadratic. Here's a logistic regression. We would use this if we had binary data, so 0, 1, yes, no, presence, absence. In this case, you can use the GLM function in R. It says possibly more after spring break. That's because I stole this slide from a previous semester because I thought it had good graphs. We are definitely not going to do more of this after spring break. I'm sorry I didn't update that. That is not great. So one thing that you need to note, this is the very last slide. So I'm just going to actually stop sharing my screen so you can like listen to me. We just talked through linear regression and we didn't talk about the statistical tests that go into it at all. That stuff is all in the lab that's posted on Lyceum. And I'm actually going to pull it up for you if I can get it to load. I can't get it to load. The most important part of it is that when you're looking at a linear regression and trying to interpret it, you need two things. You need a p-value and an r-squared value. And I haven't shown it to you yet. I'm working on pulling it up for you right now because I want you to be able to see it. Okay, here we go. Let me show you what that looks like. So this is a different website that I've built that's really similar to the one you're going to see for your class that shows how to do a linear regression. In R, you're going to do a linear regression as you see here. Let me get my annotation out. So I named it LM1 just because I wanted to give it a name. I ran my linear regression, the relationship between the length of my sepal and the length of my petal using data from Iris. When I run the summary of that, it spits out this whole big complicated table, which is all what you see down here below the call. So it spits out all this stuff. A lot of it means a lot of things. A lot of it is confusing. I don't need you to care about really any of it. I want you to look down here. The F statistic underlies the p-value. We're going to talk about F statistics when we get into ANOVA. There's this many degrees of freedom. The p-value here tells us whether the relationship is significant or not. P less than 0.05 means that it is. There's a significant relationship. And the strength of that relationship and direction is measured by the R squared. Now there's two different R squareds here. There's the multiple R squared and the adjusted R squared. I don't need you to worry about the details. I want you to use the adjusted R squared to interpret in this class. A slightly more conservative estimate. The details don't really matter. If you really want to read about that, there's a chapter on linear regression in the textbook that can tell you all about the difference between multiple and adjusted R squareds. But you can see we have a significant p-value and we have an R squared of 0.75. So there's a relationship here. It's positive and it's probably pretty good. Let's keep going and we'll see this play out a little bit more. So here we are taking the same data as you know how to do in ggplot, and we're plotting a regression, or we're plotting the points as points, and then we're throwing in a geom smooth with the method LM, which makes a linear regression line of best fit with standard error built in. So that's nice. We can see that it's a relatively good relationship. There is this big gap here where there's nothing, and that's interesting. Wonder what that means. But the relationship looks pretty good overall. Okay. Now I teach you how to test the assumptions, and here's a residuals plot we can interpret, and there's a lot of detail in this about how to do all this stuff. So just if you want to take a look, this isn't necessarily the website, but the class website that we have is very similar and has the same exact same slide. I put all of the same code into our class. So check it out. Here's another example if you're interested. There's lots of ways to play around. You should have what you need if you look at both what we did in the lecture slides just now and also on this page. But again, when you're trying to interpret a hypothesis test for linear regression, you want to look at when you run your linear regression, you give it a name, then you run the summary of it, you look at this stuff. There's plenty of other stuff up here. It doesn't not matter at all, but this stuff here, this is the significant bit. You need an R squared and a p-value, or else you can't make claims, right? P-value tells us the relationship is significant. R squared tells us the magnitude and direction. It's strongly positive, right? Notably, even if we have like a pretty weak R squared, where we get a graph like that, the p-value will probably still come out significant. They often do. Linear regression is really good at finding relationships even when they're not there. So the R squared is really important, but it needs to go with a p-value. Okay. That's regression for you. We're going to dig into the details of it with the next lab analysis of variance. So don't worry about like how F statistics are calculated. I'm intentionally leaving that out for now just because like we learned how T works and it's really similar. When we get to ANOVA, I will squish through all of that and we'll figure it out together. So please remember that if you have questions, I'm here for you. I know that there's a lot of content and I appreciate that you're willing to work through it. Thanks. See you next time.